What's up, ladies and gentlemen? Welcome to this presentation. My name is Mehdi. My background spans naval architecture and subsea SURF engineering, and fatigue assessment of dynamic flexible systems has been a core part of my work. In this presentation, I will introduce the basic engineering principles behind wave-induced fatigue in subsea risers and umbilicals, and I will walk through a practical OrcaFlex workflow for those who are interested in understanding how this analysis is performed in practice. The aim is not only to explain what fatigue means in a subsea context, but also to show how the load cases are prepared, how the dynamic simulations are carried out, and how those results are later converted into fatigue damage and fatigue life in OrcaFlex. To make the workflow easier to follow, I will use a lazy wave subsea umbilical connected to an FPU as the example throughout the presentation. So, let's begin. This is the roadmap for the presentation. I will start with a short introduction to fatigue and the main fatigue sources in subsea systems. Then I will discuss what must be ready before a fatigue analysis is meaningful, including model readiness, load case definition, and fatigue setup data. After that, I will describe the OrcaFlex workflow, the structure of one fatigue load case, the practical generation of load cases using the Excel spreadsheet and text template, and finally, the fatigue post-processing steps, including damage calculation and interpretation of results. In the introduction section, I want to answer three questions. First, what do we mean by fatigue in subsea system? Second, what are the main fatigue sources that engineers normally consider? And third, what conditions must already be satisfied before a fatigue analysis can be trusted? These 3 points are important because fatigue is never just a post processing step. It depends completely on the quality of global model, the load cases, and the engineering assumptions behind them. What is fatigue? Fatigue is long-term damage caused by repeated loading. A line may survive the highest single load in the analysis, but it still fail after many repeated tension and bending cycles. In subsea systems, these repeated cycles gradually initiate cracks and consume fatigue life. That is why fatigue is often a governing design criterion. In simple terms, strength checks tell us whether the line survives now, but fatigue checks tell us whether the line survives for the intended design life. In practice, we usually consider three main fatigue sources. The first is wave induced fatigue, which comes from waves and vessel motion and creates repeated tension and bending in the line. The second is vortex-induced vibration fatigue or VIV fatigue, which happens when current flows pass a slender line and cause the line itself to vibrate. The third is vortex-induced motion fatigue or VIM fatigue, which is different from VIV because the current acts on floater and the floater motion is then transferred into the connected lines. So in simple terms, wave fatigue comes from wave and vessel motion, VIV fatigue comes from current making the line vibrate, and VIM fatigue comes from current making the floater move. In in this presentation, I will focus mainly on wave-induced fatigue in OrcaFlex. What must be ready before fatigue analysis is meaningful? Before any fatigue run, the first thing that must be ready is the global model itself. The final line geometry must be already be defined. the static equilibrium must be converged, and the same physical line discretization must be used consistently in all load cases, especially in the region that will later be checked for fatigue. The second major block is the load case definition. The fatigue matrix must represent the real mid-ocean conditions, and if we are using rain flow fatigue, then each load case must have the correct simulation file, line name, simulation period, and exposure time. We must also exclude any build-up or startup transient from the fatigue counting period. The next block is response and hydrodynamic consistency. Vessel motions, headings, offsets, and RAO usage must all be appropriate for the fatigue problem. For a lazy wave system, which is nonlinear, the selected analysis approach must also be suitable for the nonlinear response. Then we come to fatigue setup itself. We must select the correct damage calculation method and the correct analysis type. And if we use a stress factor from an umbilical or flexible, then the fatigue components and supplier inputs must be technically justified and entered consistently. The next block is the material fatigue data and the fatigue evaluation scope. That means the SN curves must be defined correctly in the correct units and assigned to the correct components. Mean stress treatment must also be a conscious engineering choice. In addition, the critical arc length zone must be identified before the run starts. The number of theta points must be selected properly, and a critical damage threshold must be set for screening and reporting. If these items are not correct, the fatigue results can look precise but still be misleading. Finally, we need to know what results and QA checks we expect to review before we trust the output. We should know which results are likely to govern, where the likely hotspots are, and whether the most damaging cases make engineering sense. Practical calculation management also matters. Large fatigue analysis can take a long time, so good file organization and sensible planning are part of good fatigue practice, especially when many load cases are involved. From this point onward, I will move from the general introduction to the actual OrcaFlex workflow for wave-induced fatigue. The key message is that wave fatigue in OrcaFlex is normally a two-step process. First, we run the dynamic load cases, and then we use the fatigue tool to convert the resulting responses histories into fatigue damage and fatigue life. OrcaFlex fatigue workflow. As I mentioned, wave fatigue in OrcaFlex is best understood as two main steps. Step one is to run the dynamic load cases, and the output of the step is response histories such as tension, curvature, motions, and reactions. Step 2 is the fatigue post processing step, where OrcaFlex reads those response stories, perform a rain flow counting or another appropriate fatigue method, and convert the response into stress cycles, damage, and fatigue life. Many people think fatigue happens during the dynamic run, but in the reality, the dynamic run only provides the input for fatigue. Let's now focus on the first step, which is the generation and running of the dynamic load cases. In a project fatigue analysis, this is where we define the environmental conditions and the model variations that represent the expected long-term operating environment. The quality of this first step determine the quality of everything that follows. This slide explains why we usually select irregular wave time domain fatigue for a lazy wave system. Use irregular wave time domain fatigue when the problem is wave driven, the system is nonlinear, and realistic stress histories are needed for rainflow counting. That is typically the case for lazy wave risers and umbilicals because their response depends on geometry, buoyancy, sag and hog bends, touchdown behaviors, and seabed interactions. Spectral or frequency domain fatigue is more appropriate when the problem is sufficiently linear, response PSDs or RAOs are available, and a faster statistical estimate is acceptable. For irregular wave time domain simulation, each fatigue load case is the time domain analysis includes one C state bin, one wave direction, one current data set, one mean offset, and one RAO set, one random seeds, and one simulation duration. So each case is a defined combination of metocean and vessel motion conditions. It is very important to remember that this step produces response stories only, and this stage Orcaflex is not yet calculating fatigue damage. It is simply generating the tension and curvature time stories that will later be used in the fatigue tools. The case study used throughout this presentation is based on a lazy wave subsea umbilical connected to a floating production unit. The model is intentionally generic. The wave-induced fatigue methodology demonstrated here is independent of any project-specific geometry parameters such as line lengths, diameters, and drag coefficients. And configuration details vary from project to project and are not the focus of this presentation. What matters for this workflow is the method itself, how load cases are structured, how dynamic simulation are executed, and how fatigue damage is calculated and accumulated, regardless of the specific system you are analyzing. That said, in any real project analysis, the Orcaflex model must be built with full project fidelity. This includes water depths, seabed properties, structural cross-section data for subsea line, marine growth, bend stiffener characteristics, buoyancy module data, hydrodynamic coefficients, vessel RAOs, vessel offsets, and any additional components such as tether clamps or holdback assemblies. The methodology shown here applies directly to all of those cases. Before we can run any simulation, we need to define our load case metrics. The information presented for the example is for illustrative and training purposes only. Some of the data are general, estimated, or derived from available sources and should not be considered project specific, optimized, or directly transferable to other applications without appropriate engineering review and validation. In this example, we have 25 C states combined with 8 wave directions, which gives us 200 time domain dynamic simulations in total. For each load case, the corresponding C state parameters, including significant wave height, peak period, and John Swab gamma, along with the current profile with Wave heading must be updated in the OrcaFlex model before running the simulation. As shown in the table, HS ranges from zero point 0.5 meter in fatigue beam 1 up to 12.5 meter in fatigue beam 25. Given this wide range, it is common practice to use multiple sets of vessel motion RAOs rather than a single set across all C states. In this example, two RAO sets are used, one for HS less than 5.5 meter and one for HS greater than or equal to 5.5 meter, reflecting the amplitude dependent nature of vessel motion response, which is widely accounted for in wave induced fatigue assessment. To make the example as illustrative as possible, I have tried to include a relative complete set of input data covering wave parameters, current profiles, vessel offsets, and two sets of vessel motion RAOs. The intention is to show how these different input types are organized in the OrcaFlex spreadsheet and to give a more realistic picture of what a wave-induced fatigue load case matrix typically looks like in practice. Of course, in real project, each of these inputs would be derived from project-specific MetOcean data, vessel motion analysis, and the agreed basis of design, but the structure and logic of how they fit into the load case generation remains the same. In addition to this information, we also need the probability data from the scatter table as shown. It tells you how often each C state occurs over the field life. Without it, you can calculate cyclic stress ranges from your simulations, but you cannot convert them into cumulative fatigue damage. For this analysis, the 200 load case files are not created manually. Manual generation at that scale would be time consuming and highly error prone. Instead, we use the OrcaFlex spreadsheet together with a text template file to automate the process. The approach is based on a single verified OrcaFlex based model. Uh, this base model contains all the data that remains constant across every load case. The umbilical, for example, the umbilical configuration, bend stiffener data, seabed properties, vessel objects, and general simulation setting. Uh, and importantly, all 25 current profile corresponding to the 25 C states, as well as both vessel motion RAO sets, are predefined within the base model. The spreadsheet doesn't redefine this data. It simply references the correct current data set and RAO set by name for each load case, and OrcaFlex activates the appropriate one when generating each variation file. Each row in the spreadsheet corresponds to the load case and defines its variable inputs. For example, wave directions, significant wave height HS, uh, peak period or TP, John Swab gamma, the activate current data set, the mean offset, yeah, decomposed into X and Y components, and the applicable vessel RAO set. For example, for uh, the first row generates the load case one with a wave direction of 90 degrees, HS equal to zero point 0.5 meters, TP equal to 3.35, gamma is 1, current profile bin 1, and vessel offset components computed from a total offset of 1.65 meter, and RAOs 1 as the selected RAO set. The spreadsheet columns are mapped directly to placeholder in the text template file. Variables such as this is the text template file. Variables such as model, wave direction, HS, gamma, TP, active current, offset X, offset Y, and vessel type. When the create text data file command is executed from the Excel tab in Excel Orcaflex spreadsheet, Orcaflex substitute each placeholder with the corresponding value from the row and generates one complete variation data for data file per load case. One important practical note is that the base model file, the spreadsheet, and the text template file must be located in the same folder for the relevant file path to resolve currently during load case generation. This is how the project requirement is converted into actual Orcaflex simulations. One important point is that this workflow doesn't necessarily require a separate Python script if Orcaflex is properly installed and licensed on your computer, and the Orcaflex Excel add-in is enabled in Excel. The load case text data file can be generated directly from the spreadsheet by clicking the create text data file command on the Orcaflex tab of the Excel ribbon without writing any additional script. After generation, we don't immediately trust all file blindly. We first open if you generated that file and check that the placeholder have been replaced correctly. Then we open some representative cases in Orcaflex and check the wave direction, HSTP, gamma, and active current, vessel offsets, and selected RAO set. Only after this QA check, uh, we run the full batch of the simulation. After the dynamic runs, Orcaflex gives us time histories of tension, curvature, vessel and line motion response, and other local response quantities. These are the fatigue inputs. They are not fatigue results in themselves. The next step is to take these histories and use the Orcaflex fatigue tool to transform them into stress cycles, damage, and life. We now move to the second step, which is the fatigue analysis itself. In Orcaflex, this is access through results, then fatigue analysis. The fatigue tool is essentially a post processor. It doesn't create the physics of the line response. It takes the response from the dynamic simulation and evaluates fatigue damage based on the selected method, analysis type, components, SN curves, simulation period, and exposure data. Regarding the title page in Orcaflex fatigue form is mainly for identification and organization. It doesn't affect the fatigue calculation itself, but it it is still useful because a fatigue study can include many files, revisions, and alternative setups. Good naming and documentation are part of good fatigue QA. Here we select the damage calculation route. For a metal riser, homogeneous pipe stress may be appropriate because Orcaflex can work directly with the pipe stress result. For umbilical, flexibles, or steel tube component, for steel tube components inside a more complex cross section, the usual choice is the stress factor method. And regarding mooring, for mooring fatigue is a different approach based on tension range and TN curves. Histograms uh, don't calculate damage at all. They only provide cycle distributions for later use. And shear 7 is used when VIV damage is calculated externally. And externally calculated stress is used for special cases where stress recovery is done outside the standard stress factor route. For this example, which is an umbilical steel tube fatigue assessment, the normal choice is stress factors. Here we choose the fatigue analysis type. For the lazy wave fatigue problem, the appropriate choice is rain flow because we are using irregular wave time domain simulations and we need realistic stress histories. Spectral fatigue would be more suitable for a sufficiently linear system. Since this example is nonlinear and response history based, rainflow is the correct engineering choice. Regarding units, the units page is extremely important because all fatigue inputs must be consistent with the selected unit system. In particular, the SN curve parameters must match the stress unit shown in OrcaFlex. If the fatigue stress is in kilopascal, then the logarithm A value must be in kilopascal base form. If the fatigue stress is in megapascal, then the megapascal base values must be used. A unit mismatch here can produce a completely wrong fatigue life, even if the rest of the setup is correct. On the load case page, each dynamic simulation is linked to a fatigue exposure. Here, since this is a training case, I linked only the fatigue bin 1 dynamic simulation. Regarding the simulation period in OrcaFlex, rainflow fatigue analysis, the fatigue simulation period is defined as a period taken from the pre-run simulation file. So it can be the whole dynamic simulation or only a selected part of it. So the fatigue analysis period must be within the time range of the dynamic simulation file. It cannot be longer than the simulation you ran. The key concept here is that exposure time is calculated from the design life multiplied by probability of occurrence of the particular C state and direction combination. So the dynamic simulation provides the response history while the exposure time provides the long-term waiting. This is how rare, but several cases and frequent but mild cases are combined properly in the fatigue calculation. Regarding components, Orcafolix computes stress for each component using the formula that I highlighted in the slide, where KT is tension stress factor, KC is curvature stress factor, T is effective tension or wall tension, Cx and Cy are curvature components. So if the supplier calculated Kt using effective tension, then in Orcoflex you must select tension variable equal to effective tension. And if the supplier calculated Kc using wall tension, then in Orcoflex you must select tension variable equal to wall tension. And this slide highlights what must come from the supplier or from the detailed cross-sectional fatigue basis. The supplier must provide the tension stress factor Kt, the curvature stress factor Kc, the component or layer to which they apply, the tension variable used in the derivation, and the SN curve associated with that component. Without that information, the component level fatigue damage in Orcoflex cannot be set up consistently. It should be noted that for a small diameter umbilical steel tube, DNV-RPC203 provides fatigue criteria that may be used to define the SN curve, provided that this approach is accepted by the supplier and is consistent with the project fatigue basis. The analysis data page defines where along the line Orcoflex will actually calculate the fatigue. That means the arc length intervals, the number of circumferential theta points, and the critical damage threshold used for reporting and highlighting. This setting determines the spatial coverage of the fatigue evaluation. Regarding the critical damage is allowable cumulative damage for the design basis. For example, use zero point 0.1 if your project allowable damage is zero point 0.1. Use 1 if your project allowable damage is 1. It should be noted that the critical damage doesn't change the fatigue calculation. It is only a warning. It is only a warning or highlighting threshold in the result. And Orcoflix states that the critical damage sets a warning level. If the total damage at any fatigue points exceeds this level, that damage is highlighted in the results. Regarding the number of thetas is the number of fatigue points checked around the cross section. Orcaflex distributes them uniformly over 360 degrees, so increasing this number improves circumferential coverage of fatigue damage. Number of 16 is a good choice for circumferential resolution for final checks. In general, the critical fatigue location in a lazy wave riser or umbilical are the hang-off region, the sag bend, the hike bend, and the touchdown region. Therefore, a selected arc length intervals should be defined so that they fully cover these fatigue critical zones. This slide presents the main hotspot regions considered for fatigue assessment. It shows their approximate arc length location together with proposed arc length intervals to be included in the fatigue analysis. Based on the arc length evaluation, three main fatigue intervals are proposed for this example: the band stiffener region, the sag and hug band region, and the touchdown zone or TDZ. To define the SN curve in Orcaflex, there are two ways: specified the SN curve using parameter or a table. In terms of using parameters, Orcaflex uses the SN curve in mathematical form, and for this example, the curve is bilinear. The low cycle branch and the high cycle branch each have their own slope and intercept. In the Orcaflex parameter form, the general equation is logarithm base 10 of n equal logarithm base 10 of a minus m times logarithm base 10 of s, where n is the cycles, the number of cycles to failure, and s is the stress range. The region boundary defines where Orcaflex switches from the low cycle branch to the high cycle branch. So using parameters method to define the SN curve, we need the M1 and M2 and logarithm A1, logarithm A2, as well as the region boundary. This slide shows the DNV-based bilinear fatigue formulation used to derive the Orcaflex parameters for a small diameter umbilical tube. The DNV equation is first written in terms of stress range and thickness correction. Then it is rearranged into the Orcaflex form so that the slope m and the intercept logarithm a can be entered directly. If the stress in Orcaflex is in kilopascal rather than megapascal, the intercept must be adjusted accordingly. The region boundary for this bilinear curve according to the DNV equation is 10 to power of 7 cycles. This slide shows the actual example values entered for the tube wall thickness and the corresponding bilinear parameters. The key message here is not only the number and the numerical values themselves, but also the discipline needed to match the wall thickness, stress unit, and the code bases consistently. For training purpose, this is a good example of how the theoretical SN curve SN equation is translated into Orcaflex input data. As I mentioned earlier, Orcaflex allows the SN curve to be defined either by parameter or by a table. In the table method, the user enters pairs of cycles to failure and stress range. Orcaflex then interpolates between these points to define the fatigue curve. This method is useful when the supplier provides fatigue data as discrete SN points, or the curve doesn't need to be entered in parameter form, or the user wants to reproduce a curve directly from a code, test report, or supplier document. In this example, the stress unit is kilopascal, so the stress values in the table must also be entered in kilopascal. The results tab controls how fatigue results are reported. Output load case tables exports a summary table of each load case. Output details load case tables includes more detailed results for each fatigue location. Load case damage units defines how the damage is reported per hour, per day, per year. In this example, the results are reported as damage per year. Once all fatigue input data are checked, the analysis is run using the calculate command in the Orcaflex fatigue tool. At that point, Orcaflex processes each fatigue load case, performs rainflow counting for the selected simulation period, applies the SN curve, scales the damage using the exposure time, and then sums the damage over all load cases. After the calculation, the next task is interpretation. The fatigue results are not useful unless we understand which locations govern, which load cases are most damaging, and whether the pattern of damage makes engineering sense. In a real project, we would always compare the outcome with our expectations from the model behavior before accepting the final life. Orcaflex presents fatigue results in both graphs and tables. By selecting the required arc length interval, the corresponding damage and fatigue life distribution can be examined, allowing the critical fatigue zones along the line to be identified. It is important to emphasize that this example was prepared for training purposes. Several input parameters were estimated and may not be sufficiently accurate for a real project application. Furthermore, the analysis shown here was carried out only for fatigue bin 1. Therefore, the presented results should be treated as illustrative rather than definitive, and they should not consider accurate final damage results for design assessment. The typical results include fatigue damage or life plotted against arc lengths, as well as tabulated results for each load case and each fatigue point. The important the important output are the governing arc lengths, the governing component, the governing load case, and overall fatigue life. As at this stage, uh, as a subsea at this stage, a subsea analysis engineer should always ask whether the results are physically reasonable and whether they reflect the expected behavior at the bend stiffener buoyancy section and touchdown zone. This brings us to the end of the presentation. Thank you for your time and attention. I hope this session has helped clarify the wave-induced fatigue workflow in Orcaflex, especially the difference between dynamic response generation and fatigue post-processing. The key message for anyone interested in learning fatigue analysis is that a good fatigue assessment begins long before the fatigue tool is opened. It relies on a sound model, a complete load case matrix, consistent stress recovery inputs, and careful engineering review of the final results. Thank you once again for joining me, and I hope you find this presentation helpful. Goodbye and all the best.